in this lesson, we're going to go through the bouncing ball animation problem. Now, on its surface, the bouncing ball seems to be a very simple animation, but there are many things that you can do in this that can actually trip you up along the way. It's a really good exercise to work out how best to approach an animation system and what are the best techniques to use. The first thing we need to work out is what medium are we actually animating this for. In this example, we're going to animate for film, and that has a whole bunch of information that we now have to work through. Film runs at 24 frames a second. And what that means is every second of film, there are 24 frames that we might need to draw. So if you imagine a ball has been thrown and it's moving across the screen here, if we were going to draw each frame of the ball's path, we might draw this frame here. The ball's here in frame number 1. And then as the ball progresses, we get to frame number 2. And then by frame number 2, here is the position of the ball. And then maybe again, by frame 3, the ball's here. And by frame 4, the ball has got to here. And by frame 5, it's here. And by 6, it's here. And of course, by 7, it's here. So this has told us something about the system. We know that the ball has traveled across the screen in only 7 frames. And so we know that that has happened in far less than a second. Now, if we were to draw that same system again, maybe someone has thrown a different ball, and this time the ball travels like this. You can see that the ball will take many, many more frames to get across the screen. So what that means is the ball is actually traveling slower, because it will take longer for it to get across the screen than the original one. So this little example shows you something really important about animation. Animation is all about timing and spacing. So being very clear about the number of frames that you're working with in any animation moment versus the distance between each frame, so from here to here. That tells you something really important about the system. So as an example, in both of these traveling moments with the ball, the distance between the ball is relatively equal. So from frame to frame, the distance is quite equal, and on this one it's pretty much equal. So that tells you that the ball is traveling at a constant rate. If, on the other hand, we had a ball that did this, you can see that the ball moves slowly at first because it travels less of a distance per frame. But then as each frame goes, it's getting further and further apart, which means that it's getting faster and faster. The ball is, in effect, accelerating. So again, timing and spacing in animation is the key thing to understand here. And so the bouncing ball animation task is all about learning about the timing and the spacing of each of these frames that you want to put down. So in order to do all of that, we need to have a good approach. We need a technique in which to break down this animation system. Now, one of the ways you could approach it is like I did with the first example, where you start with the first ball, and then you move to the second and the third, and you just keep drawing. This is what we call straight-through animation. Basically, you start at the start and you just progress all the way to the end. And the problem with this particular approach is that if you make a mistake, like let's say I've just realized that this particular ball is absolutely in the wrong position. That means that I'm going to have to erase all of these ones that I've just drawn and start again, because all of this system is connected. So this is a highly inefficient way of approaching the bouncing ball problem, because it means that you don't necessarily understand all the things about timing and spacing that you need to, and every time you try rework it, you're going to have to redraw the whole system. So there's another approach that works better. If we look at this system, we'll see down here is where it bounces, and then it bounces again down here, and it bounces again down here. And if we draw a line straight down here, we could say that this is equivalent to the start position. So this is frame 0, where the ball starts. And if I look down here and I know that I'm running at 24 frames a second, I can work out how many frames I might want it to take for the ball to drop. So I could have chosen, for example, 24. So maybe it takes 24 frames for the ball to get all the way over here. And that tells me that because we're running at 24 frames a second, this would take 1 second for the ball to get to this position. And then I can move on and I can go down here and I could say maybe because this is less, it's a shorter bounce and it's a shorter distance, that might take less frames. So let's say it could be half of that and we could go with 12 more frames. So this would be 36, which is 24 plus 12. This is 36 frames. And then we go down to here and we say this is 6 more, so this is 42. So this is 24 frames, this is 12 frames, and this is 6 frames, because each time it's getting shorter and shorter. So you can see that I haven't started with drawing a ball. What I've started with is how many frames do I need in this system? And if I look at this now, I can see that this is almost 2 seconds worth of animation that I need to do. So before I even start drawing a ball, I've completely worked out the timings in my system. So again, reiterating that really important idea that animation is all about timing and it's all about spacing. Now, I look at this and I say, well, 2 seconds is way too long. This ball is not that important that I want to watch it bounce for 2 seconds. So I might then decide to erase this 24 and let's halve the system. We'll say 12 frames is what I actually want. So instead of 24, this is 12 frames. And instead of 12 frames there, this is 6 frames. And so this now becomes 18, and then we'll make this 3 frames. So this is 21. So I'm arbitrarily choosing these, but you can see there's a logic behind why I've chosen these distances, or these frames, should I say. So I've chosen 12, but I know that it's going to get less of a high bounce. There'll be less time it takes. So this might take half a second now to get there. And I know that it's not going to take half a second to get up and down there because it's less of a bounce and you can see it's traveled less distance, which is why I've chosen fewer frames to achieve that in. Again, the timing of the frames gives you the time on screen. Okay, so I've decided that I'm happy with the idea of 12 frames for the first bounce. Now, before we can actually start drawing, now we need to break down what's actually happening in the system. What is the physics of what's actually going on with this ball? So if I go to the ball and I choose this as my start point, I know 2 things about the way this ball is traveling. The first thing is I know it's traveling in this direction. And I also know that it's going to start traveling in that direction. In this system, I've decided that there's no such thing as friction. And so in the direction of this travel, of this arrow, the ball is going to move at a constant rate. And if you remember the original example I put up, a constant rate means that the ball will always be placed at an equal distance for every frame. So as the ball travels in this direction, it's going to move the same distance every time in this direction. So if we look down now at our 12 frames, we know that the ball will travel 1/12 of that distance. Now there is a lot of math going on here, and it might be overwhelming. But these ideas, the idea that timing of frames and distances moved have to be measured and controlled very carefully, this is what animation is. So there's a drawing aspect which is very important in animation, but to make something actually move properly on screen, you have to think about the timing and the spacing. So in order to work this out, you know that there will be 12 frames in between, and I'm going to draw very quickly, and you're going to see what will happen if you draw quickly like I'm doing. The problem with the system that's been created is that it hasn't got accuracy. I've free-handed the distances, and so things in the system are not working as they would correctly. And even though it's close, you'll find that with animation, you have to be very technical about where you put things. So instead of free-handing where the distances are, you have to measure. You have to know the exact distances between the ball. And on screen, you can see the results of free-handing. This is not a system that looks like a smooth bouncing ball. The ball is accelerating towards the end, but the balls are not separated correctly. The system does not look like a bouncing ball system properly. And that's because my approach has been very, very quick and very, very freehand without measurements or proper thought. Now, instead of me redrawing this and showing you a great system of how it should look like, I will instead show you how a master might present this. So these are drawings that you're looking at by Richard Williams. Now, Richard Williams, again, is one of the greatest animators that's ever been, and this is how he would approach drawing a system. And you can see that he clearly defines his frames, and he clearly defines the positions of the balls. He's thought very carefully about each one of these moments, and it's a very technical representation of how a bouncing ball might look.